This is a special Future States that I'm really happy to be here to introduce. As you all are aware, unless you've been asleep under a rock or something, I suppose, we won a pretty big thing a couple months ago. One of these energy innovation hubs, one of the 5 that Secretary Chu introduced. Our particular win was in batteries at the so-called Joint Center for Energy Storage Research. It was a really, really terrific win for the lab, and there's many people in the room here, actually, who deserve credit for helping get us there. It was great from the perspective of what it would allow us to do with battery, in terms of innovation in batteries, doing the basic science to innovate on batteries, and particularly think beyond lithium-ion, and George and Jeff will talk about that a lot more. But also, I think, a model for how one goes about competing and winning these kinds of projects. And they may talk about that or may not. If they don't, you should ask them questions about what worked and what didn't, because there was lessons on both sides, I think. And also, perhaps even more broadly and more exciting to me is when you think about these large partnerships of public sector and private sector, is it a model that we can use to drive science and innovation in other areas? And I think you know my bias would be yes. But as you're listening today, think about that as well. You know, think about the exciting work that they're going to tell you about and the opportunities that lie there. And if you're interested, how you might engage. But also think about how we might take this model and with the necessary evolution and tweaks, think about how we might do it in other areas of the laboratory. You're going to hear a lot more, I think, from George and Jeff about the team and all of that. You've heard words like Dream Team put to the team that was put together by these gentlemen, and I think that's true. You'll see it's a large team, which makes their lives somewhat complex sometimes, but they're doing a wonderful job of standing this hub up. I guess as of a couple weeks ago, they now officially are moving forward. They've left startup and they're into actually doing research and development, so now the fun begins. But they're going to tag team it today, so you're going to hear from both George and Jeff, which really form the really senior team, along with two other deputies that are driving this across all the institutions. So I'm going to introduce briefly each of them, and then they're going to tag team it in some way. I believe George is going to go first, and then Jeff's going to come up. So first, George Crabtree. I think everybody in this room probably knows of George Crabtree. He's a distinguished scientist here at the laboratory, as well as a professor of physics at the University of Illinois at Chicago. Have many awards through his career, including being, most importantly and most significant, a member of the National Academy of Sciences. Awarded multiply by the University of Chicago, by DOE, R&D 100 awards. I could go on and on and on. But a tremendously distinguished scientist. And I should say that the day that we were able to convince George, was it a convince? To actually come forward and lead this hub was the day, candidly, that I said, oh, we're going to win. We had a great team, but bringing George on to be the director was really the one that really cinched it for us, and sure enough, we won. So thanks to both of you for that. So George, again, research in superconductivity is renowned, published more than 400 papers, heavily cited. Jeff, and I said I would tell a joke, Jeff dressed up for y'all today, so he wore a coat. So did Matt. Matt dressed up too. Yeah, so George has a tie on at least. So we're good with that. So Jeff's done many things. PhD from Georgia Tech, worked in industry a lot, and he often, when he introduces himself, he often remarks that he's worked in industry, but he's also done something that's important when you're in industry, particularly in the startups, is you fail. So he's been in a couple startups that have actually not gone well, and you learn a lot from that. That's sort of that's the way that that ecosystem works. Joined the laboratory a few years back. Actually started working in tech transfer. Worked extensively with the battery folks on their IP portfolio. We convinced him to leave tech transfer and move into the broader program side. He's run the energy storage initiative for the laboratory really since the time that we established it, and done a wonderful job with that. Was the department head for the battery department before we pulled him out of that and put him onto the hub competition, and now he's the deputy in the hub. So these two gentlemen are a great team. They bring really interesting complementary skills, experiences, and I think you'll find this whole this whole talk very interesting, very exciting, and enjoy listening to both George and Jeff. And so with that, let's welcome George and Jeff.
Thank you. That was a great introduction, Mark, and I want to say at the very beginning what a pleasure it is to work with Jeff, who really deserves a lot of the credit for putting the team together and dealing with the complexities. And I've enormously enjoyed the win, of course, as we all have, but especially working with Jeff. So here's what we're going to talk about, a little bit more beyond these three things, but these are the three main things. The opportunity, why are we doing this? The outcome, you may have heard our slogan, 555, and I'll tell you what that means if you don't remember. And then the three legacies that the hub is going to leave. And this really influences everything that we do. So if you just know that one line, 555, and the three legacies, you understand the hub pretty well. And then a little bit about the impact on Argonne and Chicago. And I have a few slides that are maybe on the technical side about batteries, which I'll either go through very quickly or perhaps just skip them. So here's the opportunity, the Battery Development Challenge. And if you look at this ellipse on the right, you see that's the energy that we used in 2009. It comes from EIA. The two biggest elements are transportation here, 29%, and electricity broken into three pieces that add up to 40%. So that's about 70% of our energy. And it's a little bit unusual to have an opportunity to affect 70% of our energy with one effort, but that's what this is. So both transportation and the electricity grid are poised for a transformation. Transportation, obviously electric cars. So let's take foreign oil and substitute it with domestic electricity. You need a good battery for that, and we think you need a battery that goes about 5 times farther than the present batteries. That's the first 5 of our 555. The electricity grid is already in transition from coal to gas to wind and solar. Wind and solar make up about 2% of the electricity we use in the US. There are mandates that they should make up 20% by 2020. And there's no reason why they couldn't make up 30 or even 50%. The abundance of supply in this country is that big. But if you're going to do that, you need to be able to store energy, obviously, because you can't afford to have a calm day or a cloudy day when wind and solar are supplying 30% of your electricity. So the bottleneck for both transitions is inexpensive, high-density electrical energy storage, and that's what JCESR is all about. So here's our targeted outcomes. I said 555. 5 times greater energy density, 1/5 the cost, do it in 5 years. And those are really stretch goals. Every time we present this, we hear, that is pretty aggressive. Are you sure you can do that? There's 2 answers to that. First answer is, if you shoot for less, something that you think is more like, take the risk out of it, make it more likely that you can actually do it, it won't be transformational. So if your goal is to really be transformational, that's what you have to do. And we decided to face the issue and not shun it to the side and say we'll do something less. We want to shoot for the target that we need. The second answer is that if you take the back of an envelope and a pencil and figure out if I did everything right and all the laws of physics were with me, what could I get? And the theoretical answer is a factor of 10. So most mature technologies get about half the theoretical expectation. So a factor of 5 is actually reasonable from that point of view. So it's well within range. This is all categorized here and documented. I won't read those things, but we know exactly what our goals are in terms of energy density, cost, and other things. And here are the 3 legacies. So what do we hope that JCESR will leave? As I said, if you understand these 3 legacies, you understand JCESR and you understand the challenge. So the first legacy is a library of fundamental knowledge. When you're going for 5 times the energy density, you won't get that from lithium-ion batteries. In spite of the fact that it's clear lithium-ion are the best batteries we've ever seen. They power our cell phones and lots of other things, even some cars, most cars. And you couldn't ask for a better technology, except that it improves at about 5% a year in energy density. So if you're looking for a factor of 5, you have to go somewhere else. So JCESR focuses beyond lithium ion. That's where we're looking. And in that space, we don't really understand the way batteries work as well as we do the lithium ion space. So lithium ion batteries have been around for about 20 years. We understand them pretty well. But in the beyond lithium ion space, it's that fundamental knowledge which is missing. So our first legacy, a library of fundamental knowledge, atomic and molecular understanding of battery phenomena and materials. And even in the lithium ion space, our understanding is not really down to the atomic and molecular level. It's much more empirical. The second legacy, pre-commercial prototypes for the grid and transportation, at least one for each, that will, when scaled to manufacturing, be able to deliver the 555 goals. And the third one is very important, a new paradigm for battery development. Build the battery from the bottom up based on the fundamental knowledge that we're going to discover in Legacy 1. Think of the whole system as a unit, so bring it all up at one time and have end-to-end integration of discovery science on one side, prototyping and manufacturing on the other side, and let them talk to each other. And that's a new idea for the battery R&D. So here's how conventional battery R&D works. There's two communities, the science community and the engineering community. They each operate pretty effectively. New knowledge on the science community, which appears in papers, literature, the literature, scientific literature, and in workshops and lots of other ways. They talk to each other very well. The engineering community, whose outcome is really stuff, it's technology. So there's lots of literature and information there too, but the main thing is let's make a battery. And as I was saying, that battery, the lithium-ion batteries improve at about 5% per year, but they don't talk to each other well enough. So here is the JCESR picture. And on the left, you have discovery science. We have 3 concepts, which are listed here. I'll tell you what they are in a minute, plus some cross-cutting science to understand how they work, the fundamental phenomena and materials. Then systems analysis and translation, build the battery on the computer. So model A, how will it perform? Will it meet our 5 times energy density target? B, what will its manufacturing cost be? Will it meet our 1/5 the cost target? And if it looks promising, we'll send that to the right and prototype. So we might get, for example, 20 ideas coming from the left with the new discoveries we'll make. We'll model them all on the computer. Maybe 4 of them will move over to cell design and prototyping, and the other 16 we'll send back and say, it didn't work as well as we thought. Here's the weak link. You science guys, make that better. Here's the problem you have to work on. So we're going to generate science problems from this building the battery on the computer and send them backwards, as well as take ideas that come from the left and evaluate them for sending to the right. There's a dotted line there between commercial deployment and cell design and prototyping. So JCESR will not do manufacturing. But we do have manufacturing partners, and we want to be talking to that manufacturing community continuously from the very beginning so that that transition will be easy to do. And in the cell design and prototyping phase, we not only want to make batteries, we want to break them. So we want to find out why don't they work better. And when we find out what really is the failure mode, that also will go back to the basic science side, and we'll have a challenge for our basic scientists: fix this, make it work better. So this is very much a two-way street, and when we hand off to commercial deployment, those guys will already be on the team so that we can have their advice from the beginning. They may tell us something like, don't give us any materials from a certain class, they're too corrosive, and we'll know that from the beginning. We won't be looking for those materials, so we'll streamline the entire process. So here's the team. 5 national labs: Argonne, Lawrence Berkeley, Sandia, Pacific Northwest, and SLAC. All with strong interest in the battery community. 5 universities: University of Illinois at Chicago, University of Chicago, Northwestern, UIUC, and University of Michigan, very closely connected to the battery, to the automotive community. And 4 private sector partners: Dow, strategically chosen, Dow for their materials expertise, and especially high throughput materials. JCI, they're the biggest battery manufacturer in the world, mostly lead acid, and they want to be ready for what comes next beyond lithium ion so that they can keep their manufacturing up to date. Applied Materials, which makes most of the processing equipment for the semiconductor industry, and it turns out semiconductors and batteries share a lot of the same processing challenges: thin films, composite layers, architectures. And Clean Energy Trust, which is a nonprofit a nonprofit in Chicago who promotes entrepreneurship and startups. And we feel there will be a lot of entrepreneurship opportunities in JCESR that we would like to nurture as part of our mission. Here are some accomplishments from the team, the JCESR team over the last decade. I won't read them, but you can see we know how to do startups. We know how to develop battery technology and get the IP for it and license it and so on. Beyond the team, so the team that actually gets funded by JCESR, there are a set of about 40, I think it's up to about 45 now, affiliate organizations. So they don't get funding from JCESR, but they're interested in what we do. Things like private companies, venture capital firms, trade organizations, very importantly, the Energy Frontier Research Centers, which are associated with batteries. There are 5 of those, and research universities. And we will, for example, hold every year a big conference where we'll invite our affiliates. We JCESR folks will get up and talk and say, here's what we've done in the last year, here's what we're planning to do in the next year. And we would like our affiliates to hop up and say, I see you're working on XYZ. I know about that. I'm interested. I'd like to work with you on it, help you go faster. Or when you're done with it, I'd like to get that technology. Give it to me. Let's start talking now so we can make that transition easier. So I said there were 3 things. Let me briefly say what they are. 3 concepts for energy storage: multivalent intercalation, chemical transformation, and non-aqueous redox flow. This is a diagram of how a lithium-ion battery works. A lithium-ion goes from anode to cathode and stores and releases energy on each cycle. It has 1 charge. So if you put in something, a working ion with 2 charges, like magnesium, or 3 charges, like yttrium or aluminum, you'll double or triple the energy density in one fell swoop. So that's the first idea. Second idea is get rid of the intercalation. So the lithium ion, when it sits in one of the electrodes, is between layers of a host material. So get rid of that host material and then substitute that intercalation with a chemical reaction, like a reaction with oxygen. So lithium oxygen, lithium sulfur, sodium sulfur are examples. And because there's so much more energy in that chemical bond, you can get a lot more energy density out of the battery. In fact, the theoretical estimate, as I was saying, is a factor of 10. That's the second idea. The third idea is get rid of the electrodes. So the electrodes, because they're solids and the working ion has to go somewhere in that solid structure, gives you a restriction. You have to find a compatible pair. If you replace the solid electrode with a liquid solution or suspension, anything can go in solution, you immediately open up a much broader horizon for possible anodes and cathodes. So that's the third idea. And these are all very profitable, let's say very promising ideas. We'll certainly rely on lots of the infrastructure, scientific and technological, which is already here. So I've listed some of the things that we'll do. An electrolyte genome, I'll say a bit more about in a couple of slides. Lots of techniques, all of the user facilities like the APS and other user facilities that BES already has. And we'll integrate that. This is the point of JCESR. You have to bring it into one or a few minds to understand how it all fits together. And in the process of fitting this all together, we'll want to understand things at the atomic and molecular level, a level that is possible now to understand because of the last 10 years of nanoscience, but at which the battery community hasn't really fully embraced. So they tend to be a bit more empirical. Here is a cycle of how things may work. I mentioned before the electrolyte genome, which you see here in the materials genome. So we'll be modeling maybe 1,000 or 10,000 materials for anodes and cathodes on the computer. That will help us select the most promising ones, let's say 5 or 10 out of that 1,000. Those 5 or 10 we'll bring to our electrochemical discovery lab, which is a state-of-the-art lab where you synthesize thin films and single crystals by various techniques, so new materials. You then pass it along to characterization statements where you measure maybe 6 or 7 different properties. each one without taking the material out of its protected environment. So it might be in an argon environment or a high vacuum environment. And then you can put these things together so you can also characterize interfaces, and batteries are all about interfaces. The things that look promising will go up to cell design and prototyping, and you see the open loop that JCESR represents on our first diagram. One of the most bold and innovative things we proposed was an electrolyte genome. Some of you may have heard of the materials genome. That concept been around for about 5 years. Applies to solids, things with structures. But most electrolytes are liquids, and they are further organic liquids, which is a much bigger space of materials than you would expect for the typical solid-state electrodes. So it takes a computer to help you analyze and filter this space. So there's lots going on. So here, for example, in the upper right is a quinoxylene organic molecule, which by simply adding ligands onto, you can change from insoluble to very soluble. That's on the left. On the right, by adding a different set of ligands, you can go from no electroactivity to highly electroactive. So the design of these molecules is very important. That's one of the things that the electrolyte genome will do. Our reviewers, the written reviewers, we had 8 reviews, every one of them said, that electrolyte genome, I like that. You guys ought to pursue that strongly. So here's back to our diagram. I've already talked about building the battery on a computer, so modeling and its importance for predicting both performance and manufacturing cost, but also its failure modes. So we're going to, at this modeling stage, find out which components don't perform at the level of the others. So where's the weak link? And that's a problem we'll send back to the basic science side and say, fix this. We'll then take, let's say, out of 20, the 4 that look good, we'll send on to cell design and prototyping. And you see some prototyping equipment in the upper right-hand corner, which happens to be at Argonne. But many of our partners have 2 or 3 times the prototyping capability that, if you add them all up, that Argonne has. So this is really quite a sophisticated operation. So here's the techno-economic modeling. I've already mentioned this and maybe skip over it rather quickly. To the cell design and prototyping, where we have another innovative idea. And that idea is that the prototyping ought to be done by a team that represents every section of JCESR. So there will be basic scientists on the prototyping team. There will be battery designers and modelers on the prototyping team. Of course, there'll be prototype experts on the team, but there will also be the commercial manufacturing representatives on the prototyping team. So those 4 elements are represented by the 4 colors in that ring, and they will oversee the entire production of the prototype. So we're going to kick off another innovative idea. Instead of waiting for a battery to emerge from our research, we're going to kick off with 2 TDTs, 2 prototypes on day 1. It's already happened. One for transportation, which will be the magnesium intercalation idea. A second one for the grid, which will be the non-aqueous redox flow idea. And I should mention that both of these ideas are quite broad. But we know there's promise in them. And we're kicking off on day 1 because we want to start the process. So we want to see how it works. We want to find problems to send back to our basic scientists. And we want to get the prototyping team off to a fast start and integrated with the rest of the operation right away. So here's some of the people on the prototyping teams. They're all young, eager, ready to go people. You can see from the looks on their faces. And we're looking forward to working hard with them. Very important part of the program, the intellectual property plan, all signed before the proposal was submitted last May. And it has at least 2 interesting features. One feature is no exclusive licenses. So some of our partners were not too happy with that, but they felt that the benefit of getting what's going to come out was worth that small sacrifice. And that's the way we signed the document. The second thing is that Argonne, by agreement with everyone, Argonne will act as the licensing agent. So some outside entity that wants to get JCESR IP just needs to make one stop. And Argonne, of course, will consult with all the partners, but it's much easier that way to coordinate than making 14 stops. Here's our org chart, and very importantly, you can see that we report to the director, Eric Isaacs. And I think this is one of the, Eric has been fully bought in from the very beginning on making JCESR work. He understood how important it was and how much of a challenge it was to get it done. I think his support from the top, and Mark Peters is right there, who introduced us this morning, has been fully engaged from the beginning. So we report to the top, and I think that's very important. Then there are 3 deputy directors. So Jeff is one of them, also Ninad Markovic and Venkat Srinivasan at Berkeley. But beneath them, these are the people that are going to make it work. So we have teams that go after every aspect of JCESR that needs attention. So there are teams for each of the concepts. There's a cross-cutting science team. There's a systems analysis and translation team that will model batteries, and there's 2 prototype teams, one for the grid, one for the car. And these are the folks that are going to make it work. So each team has a PI, has budget authority and lots of scientific knowledge. Also a lead scientist who will simply advise technically on this is the right way to go or not. And it will be up to these folks to communicate this way within their teams, of course. There are 5 or 6 projects within each team, and up to the very strategic, how do we relate to the 555 outcome and the 3 legacies. So that's really the heart of JCESR. So I want to emphasize that the 3 concepts, we don't expect to get 1 battery per concept or 1 class of batteries. We expect that the battery we get out will draw from all 3 of those concepts. So here is a battery, for example, that might come out. We might have as our anode a multivalent metal like magnesium. So that's from the first concept. We'll have an electrolyte from our electrolyte genome. We'll replace the cathode with a flowable electrode. And it may be made up of, again, electrolytes and organic materials that come out of our electrolyte genome. And we'll be able to store this high energy in a big tank out in a field somewhere, so the capacity is basically unlimited. That's what you want for the grid. And pump that, the electrolyte with the stored energy back to the reactor to react with, through the electrolyte with the anode. So this draws from all 3 concepts. So I wanted to mention one more very important thing, and I give DOE a lot of credit for that. So here's our chart, and this actually matches to every part of DOE. So in this lower caption, lower stripe, you see the words that DOE uses to describe itself. So they go after Grand Challenge research. I'm interested in this because it's interesting, not because I'm going to use it for something. They go after discovery science to understand how things work, both phenomena and materials. They go after use-inspired basic research. I'd like to make a better cathode. Let's hear what do I have to do that. And everything that you see on this side of this chart is sort of discovery-based and phenomena-based. Everything on this side is performance-based. So applied research, let's make this thing actually work as a technology. And technology maturation, let's make it work better. So this spans all of DOE and gives them credit, and especially Steve Chu, for recognizing that that's what's needed. Instead of branching to lots of compartmentalized offices, it branches to the whole of DOE. So this is a bold experiment for them. It's a bold experiment for us, but it's one that really has a lot of promise, and we're looking forward to breaking the ground and helping DOE to understand how to do this. So let me talk a little, that's the second part of the talk. Let me talk a little bit about the impact of JCESR. So one impact on the lab is we're getting a new building. So the state has committed $35 million for a state-of-the-art JCESR building, which will house the Electrochemical Discovery Lab. This should come online in 2015. Before that time, we'll be housed first in Building 200 and then in the ESB before this is up. And the Electrochemical Discovery Lab will be active in both of those buildings. Second thing, if you look at the hubs, They were modeled on a thing called JEBA, Joint Bioenergy Research Institutes, one of which is at Berkeley, which has been remarkably successful. They're now in their second 5 years, so they've been renewed. And although they're looking at biofuels, a lot of the principles they embody are the same as were designed into the hubs and that we will certainly emulate. So if you look at what has the effect been on Berkeley? Well, first one, nailed the concept of team science. So sole proprietor science is not the only option. That is, you have to have a team, as JCESR does, going from discovery science to prototyping if you're going to be effective. Model the relationship between discovery science and technology transfer. We've never done this under one smaller organization like JCESR, which can really control its parts. Forge strong relationships with programs at other labs. So they all, like JCESR, work with other labs and with other commercial companies. And this, if you look at this second sub-bullet, enabled the lab to make strong responses to other new large-scale programming opportunities. And we think that this is what JCESR will do, set a standard and a model for success to make this work in the future for bigger programs. And centralized operations and support, which allows researchers to focus on science. So JCESR, that's one of the planning features that will take the administration out of it, and the scientists can focus on the technical things that they should be working on. So on industry, there are also, from JEBA, impacts. Commercialization model generated more than twice the national average of the top 5 US research universities, and there's the list of invention disclosures and so on. When you really focus on how to do this, you can do it much better, and we're hoping to break new ground there. They have 3 startups that spun out of JEBA in the first 5 years of operation, and that is a superb track record that we'll see how well we do, but that's certainly our goal. There's another impact on Chicago. There's an innovation system that's emerging now. If you think about it, we have lots of research universities eager to do startups and, and to innovate. And we have the state, which is very committed through our building and through other means. It's clear that they are. And the city of Chicago, Mayor Rahm Emanuel, has been very strong in his support of JCESR and also of innovation. So JCESR will be a big platform within this innovation ecosystem, and we are hoping to play a leading role in making it happen, and at least in the battery business, nurturing the startups. So that's sort of wrapping it all up. What does JCESR do for Argonne and the region? It's a model for thinking big, so discovery science, innovative design, and demonstration all under one organization. Addressing big societal challenges and opportunities, and this I think is what Congress and the taxpayer expects of science now. So they like that we're off playing in our sandbox and just out of curiosity wondering about things, but they also like it when we solve problems, and we're certainly capable of doing that. We're integrating across the laboratory, so you might say materials computation, X-rays, and I've left room for many other things that the lab does well. They could do it better if they talk to each other more, were integrated more, and went after the same goals. And operational support for lab missions, JCESR will certainly epitomize this. And coordinating with Chicago institutions, I've already mentioned that on the last slide. So I think with that, I'm done with my part. And I'm going to ask Jeff if he would like to come up and talk a little bit about how we won and what it means specifically for the future of Argonne. Jeff, thanks.
Thanks, George, and thanks, Mark, for the introduction. Thank everyone for spending some time on a Monday morning coming in. I really appreciate it. And of course, that meant George and I were working over the weekend, since it's Monday mornings, to give the presentation. Also, I appreciate Mark teasing me for dressing up. I did have 2 sets of clothes in this morning, and as usual, I compromised, left the tie in the closet. That was my compromise. I didn't wear jeans, though. Okay, so winning the hub, what did we do? When I look back and was actually preparing this presentation, it was interesting to note, and I think you'll see how much effort went into this, and unearthed some memories, unfortunately, of some of the dark times in putting this together. But I want everyone to keep in mind as I walk through this, we're talking about future states, and George left his part of the presentation with where I'll pick up. What are the implications of this? Not only in the science and technology side and the research we'll perform and the way we'll perform it, but how do we create big programs like this? And this is a laundry list, and I'm going to spend a couple of slides after this one focused on this first bullet. We started early and worked hard, and that seems like a stating of the obvious. But you'll see when I go through the next few slides, it might not be as obvious as you think, the details of that. And focus, I mean something really in particular, and that was that upper management at Argonne had a team focused on this, but they pulled me out of my old job and had me 100% plus dedicated to this project. And I can't stress enough with each of these bullets how important each of these were in our win. I was taken out of my old job. And I'll tell you, that took some convincing. I did not want to do that. I'm sure Mark remembers those conversations. But looking back on it, it was vital that I could spend all of my time thinking about one thing. Management supported and participated, including up to Eric. You know, Mark was heavily involved in the whole process. Eric was also involved in driving it. These next two really look like stating the obvious, but for those that have responded to funding opportunity announcements or requests for proposal, you'll recognize that often you look at the RFP or the FOA and you think, well, this isn't really what they need. This isn't really what they're asking for. I'm going to give them something different, even though it's in black and white. And we had a long series of debates about whether DOE really knew what they wanted, even though it was in black and white. So being responsive to the FOA and being compliant to the FOA are extremely important in our view. And they are different. For example, responsive means they're asking for open collaboration. So you have to put collaboration in the proposal. That's what they're looking for. That's different from being compliant, meaning they're specifically asking, in this case I just gave one example of the dozens of examples in the proposal. They specifically wanted a 3-page CV for each key person in the proposal, in the hub. And there was a definition for what a key person was, so that's what we delivered, a 3-page CV for every single person. And I can tell you, our document, when it was all said and done, was about 1,200 pages long. So this little bullet here, as small as it looks, caused enormous amounts of heartache and headache and staying up till midnight, 2 in the morning, making sure we are compliant to the FOA. Also, we hired outside consultants, and what were delivered from those consultants were capability and objectivity. Capabilities that we may or may not have inside of Argonne, people that could come in and help us with some of these bullets up here. And these last two bullets go together, in my opinion. What I learned is when you hire these outside consultants, their career is based on winning these things. They're not based on some internal political problem or motive inside of Argonne or Berkeley or Sandia or University of Michigan. They're not based on whether we're going to please a certain program manager inside of DOE. These consultants you hire outside are focused on one thing, winning. And it's very, very clarifying for you as a team member. So I can't recommend that strongly enough. Now, what did I mean earlier when I said we started earlier and worked hard? I'm going to walk you through a timeline. And there's a point to this, I promise. The funding opportunity announcement came out in February of 2012. And the due date was May. We had 90 days for the proposal, roughly. And orals were in July, so there was an oral examination we were required to give, and the win was announced November 30th. And what I'm going to leave out in my description is all of the work we did here, especially here. It was incredibly intense. And what I really want to talk about is what do I mean by started early and worked hard? Right after President Obama was elected and inaugurated in his first term, the hubs were declared. I don't know how many of you remember this. Secretary Chu was new at the time, and he announced new programs, EFRCs, ARPA-E, and the hubs. And he listed 8 hubs. Energy storage was one of them. So way back in 2009, we had our first meeting in June of 2009 with Berkeley, where we started planning, what should we do? Should this hub come to fruition? What can we or should we do? And we started working on ideas in the intervening time. That first 6 months was mostly Berkeley and Argonne batting around ideas for scientific ideas as well as what should the proposal process be. The next 6 months was developing a team strategy. This was mostly internal to Argonne, driven by Mark Peters sitting in the front row here. And then we set the team in the July to October timeframe. So you saw the description of the team by George. There are reasons behind every single one of those selections. Scientific reasons in terms of the research we'd be doing, technology development reasons, and strategic reasons. And then I had my first meeting with the consultants in November of 2010. And remember what I told you, the FOA dropped in February of 2012. So I met with the consultants the first time, towards the end of the year of 2010. And I don't know what Mark's memory is of this, but I remember clearly during the Christmas break shutdown of 2010, Mark and Eric calling me at home and saying we weren't going to wait for Congress. I don't know how much of the hub stories you all remember, but there were 8 hubs declared way back here, and Congress kind of approved of them piecemeal in the budget. And it was over this holiday break. We already had the team set. We had the genesis of a plan. Mark and Eric decided, let's not wait for Congress. So we had our first team-wide meeting in March, and we started going out to our industrial members, particularly JCI and Dow, and we learned in that process they were maybe more eager than we thought they were. And they were even willing to put up a lot of their own money and reverse the government process. We could develop a team and a proposal of work with funds and go to Washington and say, can Washington cost share? This was our plan at the time. I put this in bold because I want to call this out as something special. Remember, we still didn't know whether Congress would get its act together and a FOA would ever come out. So we got together and wrote our own funding opportunity announcement. There was enough information out there where we could make some good guesses, and it turns out we were about 90 to 95% right. And I don't say that like we had some kind of genius mechanism. All of you in the room that are looking for future programs know, I would predict, 80 to 90% of what your DOE sponsor is going to want. This exercise was critical. This is why I put it in bold here, critical to our whole process. We wrote our own funding opportunity announcement, and maybe even more importantly, we wrote our own proposal against that funding opportunity announcement and had it reviewed by an outside committee. In fact, George, this happens a lot in the world, George was on that outside committee and reviewed it. This was his first getting pulled into the gravity of the black hole of JCESR, or whatever you want to call it. First attraction to JCESR was this outside review, and we got ripped apart. In fact, one comment I really remember is you wrote, they told us, the review committee did, you wrote an excellent funding opportunity announcement. We believe it's spot on, and then you didn't respond to your own FOA. Going back to my earlier comments, we weren't even compliant. And I'm not kidding, we weren't compliant to the FOA that we ourselves wrote, which just sounds insane. Maybe it is. But it was very critical because it was a practice set. And the key recommendation they made to us was write a white paper, write a strategic white paper. In essence, what is it you're proposing? Forget the 1,200 pages. Write a 10 or 15 page paper. And it took us a few weeks, got all the team together. And I would argue to this day, when you dig into that proposal and you listen to the presentation George just made, 80 and 90% of it came out of this process here. Still, way before the FOA ever came out. On the heels of that strategic white paper we wrote, we had 7 different workshops that roughly reflect the thrust, the scientific thrust that George described in the overall scheme of JCESR. And we pulled in a wide variety of the partner set. We had a huge number of scientists and engineers from across our partner set participating in these workshops. And in case I forget to mention it later, ultimately in that last 2 to 3 month period of writing the proposal, it bore down, and I'm looking at some faces out there, to a very small number of us working 12 to 15 hours a day, which again, it gets back to focus, but it also causes a ripple effect because the 50-odd scientists that were invited for these workshops, it boiled down to about 5 or 6 of us actually writing the proposal, which is very important. The reason I mention that now is to have this long period of time to be developing and working the team because they had to trust us. And they still have to trust us to this day because we're not all together all the time. Finally, this was the first timeline I put up there. So when I say timeline, I'm talking about starting in June of 2009. Put this in perspective. When you got your PhD, how long did it take you? 4, 5, 6 years? This was a nearly 3-year process to win this big project. Okay, focus on these words right here. So what? Who cares? Is Jeff just rehashing his old wounds? No. What was the result? Of course, winning was the outcome. But the question here, and Mark and George both mentioned this, what did our process teach us? Did it make a difference? DOE told us that there were some key things that differentiated our proposal from the other proposals and our orals. The science plan, particularly integrating of the big tools across the country, the excellent team, both scientific and industrial, a fully executed intellectual property plan, and having a work breakdown structure. So having an entire 5-year-long structure that says all the work we're going to do. We proposed that. And we also put in the proposal that we weren't going to stick to that plan. This was the 5-year plan that we proposed, and part of our management process was going to be to reboot that plan every year. So what I would argue is the answer to this question is yes. Did it make a difference? In every single one of these cases of differentiation from our competitors, I would argue if we didn't spend the several years developing our plan and developing the trust amongst the team, for instance, the trust factor, there's no way, I can tell you, we would have had an executed intellectual property plan if we didn't take our time to do it. In fact, none of our competitors had that. There's no way we would have had the team. I had several team members tell me afterwards that they were recruited very heavily by our competitors, but they were already signed on to us. And I want to be clear about something. When I say we developed the team, we actually had written commitments with executives from each one of these institutions putting their name, their signature, their John Hancock on a sheet of paper. There was a professor at MIT that told me when we were in Spain together a few weeks ago that he was thankful we had him do that because MIT was pushing for him to enter their proposal, and he was able to say no. He didn't want to say yes to them, but the fact that he already signed on to our team a year in advance of being asked by his own institution, that he was able to say no because he was already committed to our team. So again, long time frame you need to be thinking about putting these things together. Okay, so back to the topic of the talk today, future state. I just want to point out that we now have in place Energy Frontier Research Centers, 5 energy innovation hubs. There was originally a plan for 8. I don't know where it will go under the new secretary. None of us can predict exactly. But there may end up being as many as 8 or 10. There are 5 today, as well as ARPA-E, the Advanced Research Projects Agency for Energy. In each one of these cases, and to my own personal surprise, even our Argonne's EERE battery program is focused on something very specific now, voltage fade. Each one of these projects is a large collaborative project aimed at something very specific, a specific outcome. And they want a big, large collaboration and an entity that can lead that collaboration. And my point is, a pendulum is swinging from our primary funder, the Department of Energy, or maybe has swung to mission focus with societal outcomes, large collaborations, and even, in most cases, industrial interest. In every case up here except the EFRCs, they're specifically asking in their RFPs and FOAs for industrial interest. And I've been telling the department at Argonne this for several years, and I'd like to tell all of Argonne, and I don't speak for Eric and Mark in this, but you might think, oh, well, pendulums swing back and forth, they're small. When I tally up the funds for all of this on an annual basis, it's about $500 million. $500 million out of DOE right now, annually, are focused on things with these criteria. And it's not advancing. There we go. So I guess my point, and my last point to make is be proactive to this future state. And you might ask yourself, what's the timing of this pendulum cycle? And by the way, this is from the Museum of Science and Industry. If you haven't been there with your kids, you'll remember one of the stairwells has this massive Foucault's pendulum in it. What's the timing of this pendulum cycle? You might think, I like doing my own thing, which is good. $500 million is still a small segment of all of DOE's research dollars. What is the momentum of the pendulum? To me, that's the better question. How big is the mass of this thing that's swinging back and forth? From my own career, I'd say this big of a shift, $500 million of research in DOE, has a lot of momentum behind it. And it's bound for that pendulum to swing back. But I would argue at a minimum of 5 years. We're looking at 5 to 10 years, in my opinion, of this pendulum swinging, especially, as George articulated, the Joint Bioenergy Institute is viewed as a resounding success. And by all measures, it is. We absolutely expect JCESR to prove a case that this is a successful swing of the pendulum. And what is it really? It's a swing back, even if you listen to Secretary Chu's own words, to the days of the Manhattan Project or Bell Labs. So it really is a pendulum swinging back and forth. This is nothing new, really, to the world of science. So my main point is we have the JCESR experience now as an institution to leverage. So please, I leave it up to you, leverage this capability now that we have at Argonne for winning and starting these big programs. I think that finishes my talk.
Yeah. Thanks to you both very much. Excellent, outstanding talk. So time for questions, please.
When is day one for JCESR?
January 1st, 2013.
Oh, so you already started.
Yeah.
Okay.
We had, Jeff can speak to this, but they told us, and it was in the FOA, 3 months to start up and be fully running. That would be April 1st. We were ready on April 1st. So we're now running.
Thanks.
I'd like to thank you both. It was a very inspiring talk. What I'd like to ask is, what can we learn as really junior PI or even postdocs? What can we learn about this process and scale that down for our own, little money projects?
That's a very good question. I guess the first thing I would do is encourage you to resist the temptation to scale it down. I think when I look at the successes in Bell Labs and the successes in the Manhattan Project, those were physicists and chemists and scientists younger than the two of us. Don't undersell yourself. And the second part of that is, if you have a certain need to scale it down, or not, leaving scale down out of the question, do your best to read the mind of your sponsor. And you can do it really effectively because you already know them. You know where they're thinking of headed, couple with them, work with them as a team, and you'll be able to help drive your sponsor's thinking. That's something we learned in this process as well, that if you're teaming with your sponsor appropriately, you can drive their thinking. So whether it's scaled down or not, I think the key is understanding what's needed, what the societal need is, understanding what your sponsor's need is. Usually those two things are the same.
I have a tiny comment on that, and that is that most problems that are worth going after now, or many of them, are bigger than one person. So in the old days, you had a professor and his students, and they were the experts in this, and they dominated or tried to dominate that part of the field. But the problems we're facing now, especially if you're looking for a solution and not just a little bit of insight, if you're looking for a solution, you need to have experts working together. And I believe that is coming. So I would encourage you and your colleagues to think about how can I talk to the guy next door and get some mutual benefit from it. So publish a mutual paper that you couldn't have done individually, but you can do as a team. That's a way of scaling it down, and of course scaling that up and up and up. Eventually you need some administration to take care of it, so that's another level, but you can do it at the individual scientist level as well.
Can I say one thing real quick? Just 1 second. I was going to say one other thing, if I may,
yes,
about that. So the timeline, Jeff did a wonderful job, and it had uniqueness to it, right? Not just scale, but the time we had. Because of the decisions that were being made or not, we had some time. But the point that he made about compliance with the FOA and responsiveness, invariably, no matter what scale, as I look at at lessons learned across the lab, a lot of times people don't focus on that. They think about, let's tell them what they really need, not what they're asking for. Jeff made that point. That's a scalable thing. I don't care whether it's a $500K proposal or a $20 million proposal. So that's one thing I would definitely call out. We don't do that very well as a laboratory. I'll make a general statement, so keep that in mind. Sorry. Lillian, were you going to say something?
Yeah, at the beginning you had that wonderful slide. Battery in the middle, basic on the left, engineering on the right. And everything started with the basic, and then kicking starting from engineering to the basic, to the point that I was under the impression that basic is actually there to serve what engineering cannot fix. So my question is, in this particular concept, or are you aware of any other big project where basic is really having some leverage to work on unrelated, conceptually new energy source or similar?
So that, of course, JCESR is dealing with batteries. So our charge is very clear, and our 555 goal is difficult. It's a stretch, so we have to put our resources toward that. But within that sphere, the basic side is looking at things that nobody thought of before. And these three concepts that I listed, so multivalent intercalation, chemical transformation, and non-aqueous redox flow, have plenty. They have things that people have thought of before, and in that sense we're doing service to understand them better, but they also have lots of space which is unexplored. And that space is also on our radar screen, so we want to look at those things as well. This may be one of the few times, and we'll see how it works, we'll refine as we go forward, but one of the few times where both of those, the service component and call it maybe the discovery component, exist in the same space and in the same mind. And I believe that they actually reinforce each other. When you understand what's wrong with the things we have now, that inspires you to innovate and discover some things that will make it better.
Prototype systems that you have defined, are they kind of rifle shot, very focused? They have the 10x potential and could get you to the 555 objectives, or are they learning platforms below the 10x conceptual and you do not expect them to get you there? You extract the learning, expect to abandon them, or is it some other thinking that drove the definition of those systems?
So Kevin Gallagher, the PI over systems analysis and translation, probably has the answer just like this, but the generic answer is both, Peter, that it is to exercise the system. And I think to the questioner upstairs earlier, we want to have both activities, the very basic science, the more applied tech development, going in parallel so the information bounces back and forth as we progress. So part of it is to exercise the system, get the scientists thinking they're part of a team that's actually going to make a device from the very beginning. But we did choose two things to prototype that will meet the theoretically could meet the 555 goals. We fully expect them to fail. In fact, that's part of the exercise. We want to know why they're failing so that we can drive the science back on the left side of the org chart. But they do both have the potential for meeting the objectives.
Question? Go ahead.
There are a lot of us who are doing affiliated research in terms of applications of energy storage, and I'm wondering if there's any formalities from the lab or from JCESR as to how we can leverage this in terms of our ongoing research. So I'm in buildings and doing grid work, so it's a matter of, obviously there's applications, that's what you're working on, but is there a way that, since we're not going to get any of the $20 million a year, that's all going toward your science, but is there a way that we can formalize, say, we're going to be working with those researchers in terms of helping you with applications or interacting with you? Is there a formal basis being set up for the other people at the lab to take advantage of that?
So let me make a comment. I know Jeff will definitely wants to comment on this, but the answer is either yes or almost yes. And if you would come up and see us afterwards, we can start that, in your case. But as it happened by pure chance, just after in January, ComEd was having a big yearly meeting where they get all of their engineers together. They have exhibitions, 100 different exhibitions about what's going on, and have talks. I got invited to that because the timing was right, and I asked them in my talk, I had planned to do this, what application do you want, you grid people? Because the grid is rich with applications for storage. It's not just solar and wind. There are lots of other applications as well. And I asked several times during the talk, and I realized, of course, that they weren't ready for the question, and I didn't get much coming back. But we will be getting things coming back. So that's an example of how we would like to know what are the uses, so that we can start to, strategically guide our research to those things that you need the most. For the car, it's pretty clear. You want it to go a long way, you want it to charge fast, and you want it to be safe. For the grid, there's probably 20 different things that you could want, and it's a question of prioritizing those. Jeff, do you want to comment on that?
Yes. So yes, that's a great example, and what we built in, if you looked carefully and saw in our org chart, we built in an office for integrating with other R&D programs. Mike Thackeray and Khalil Amin are heading up that office. But specific to your question, for example, similar to the example George just gave, we held our first EFRC meeting where all the battery-related EFRCs came to Argonne and had a workshop where we described what it is in more detail than you saw here. We're working on, the EFRCs described what they're working on, so we could look for those collaborative spaces and leverage off one another. Not just have the EFRCs leverage off us, but both ways, and I'm assuming that's in your mind as well. So we will have a formalized process where we bring in, we're going to start with an affiliates workshop, and I would say count yourself as an affiliate, because I think a lot of folks are asking us that same thing right now. Hey, we don't need money, but you may be learning things in JCESR that we can leverage. And so we're aiming for the June, July timeframe. We don't have a date set yet, for a multi-day workshop where we get to expose to each other what our work plans are, what our current state of R&D is, and then have smaller, like the ComEd meeting George described, smaller meetings where we meet with individual entities or small groups of entities. So we can imagine what we have in the proposal is an annual cycle of a massive workshop with all of our affiliates, and then one-off meetings during the course of the year as well.
One final question? Sure.
So this question for George. In your presentation, you showed that chart several times, and you said that currently there's a lack of fundamental understanding at the atomic and molecular level about batteries. And at some point, though, in the process, you plan to use computational simulations and modeling to evaluate the performance of your batteries. I was wondering, how much are those simulations based on fundamental understanding of the batteries themselves? And isn't this a kind of a
great
loop
question
that you need to close?
So certainly everything that has the word genome in it is based on atomic and molecular level understanding. So those are DFT codes, and there are atoms in there, and how the atoms interact with each other to make a working system is fundamental to those codes. So that's an example of working at in the modeling space, working at the atomic and molecular level. There's lots of other things that are much more empirical. So a typical battery, Jeff will correct me, and I'm sure if I overstate this case, but I want to make a better cathode, let me try this one. Oh, it worked, let's keep doing it. Or no, it didn't work, let's try the next one, without having to go down to the atomic and molecular level and understand why did it work or why did it fail. And with that information, this is part of the JCESR approach, with that information, we can either make it work or make the next one work better, because we understand that atomic and molecular level. You couldn't have done this 10 years ago. There wasn't enough nanoscience 10 years ago to make that statement. There is now. So most things, if you try hard and spend enough money and enough effort, you can understand at the atomic and molecular level, and that's certainly a much bigger platform to work from than just the empirical understanding that we get otherwise. Do you want to comment on that?
Just to amplify a little bit, so what we expect, as similar to the way we'll have push-pull between the more basic science and the applied science, we'll have a push-pull between experimental and computational work at the atomic level. So characterizing things down to the molecular or even atomic level in some cases, as well as performing computational, developing an understanding through computational chemistry and physics of those systems, we expect that to be a fertile communication pathway that goes both ways. In fact, we've designed that into the various sub-projects of the hub.
Okay, so thanks for your attention, interest, questions, and as advertised, outstanding talk, gentlemen. So thank you.